those creation annihilation operators for the fermion system with the normal spin commutation relations, you see that these commutation relations are preserved. Okay, so that is left as an exercise. You can just substitution and trying to work out those commutation and anti-commutation relations, so that you will be able to get this back, which you know very well. So then I said that it is better to have these creation annihilation operators for fermions, that is conduction electrons, in the K space. The reason for that, as I said, is that whenever we are dealing with any dispersion relation, is always energy relation in K space, right? Although we do experiments in real space, but theory prefers to work out the energy levels in the K space. Because, why is that? Can anyone tell me quickly? Why does theory prefer to work in K space rather than work in the direct space? Yes? Any idea? Why does one have to go to the K space? Why not do everything in direct space where you are really measuring these quantities? Energy? Yeah, that is one way of putting it, but then I can still express directly energy. Why should I put it in h cross square k square by 2m? Why should I work in that space at all, K space at all? Why not in the direct space? Because I know energy is corresponding to a real system, right? I have some system on which I can make measurements, and I am just theoretically calculating energy. I can calculate energy by Schrodinger equations, right? And Schrodinger equation is written in the direct space, right? So what is the need to go to the K space? In which way? Yes, you're right, but how do you put it? It's not the lattice size. It's not the reciprocal lattice size that is important, but something else. Right. A set of parallel planes in the direct space can be represented by just one point in the K space, and that is done by the Miller indices. You know that. Okay. So that means set of parallel planes corresponding to some Miller indices, because they can be represented by one unique normal to all those planes, and that one point which will give you the coordinates of that normal to those planes is just one K point in the K space. So this gives a huge simplification. If you try to calculate theoretically, you have to do it in the K space. You have no choice, right? In the direct space, it is impossible to work with so many, say, many-body problem, as I was telling you. So it cannot be solved that way. So that's why with these operators we have to Fourier transform from direct space to the K space, and then write these operators. Now this way, I had given that for the creation operator, for the annihilation operator is this. And then in terms of these operators, the perturbation Hamiltonian, which is the Hamiltonian between the S conduction electron spin and F, the localized magnetic moment. Okay. So then this is represented in terms of the creation annihilation operators. Now what I have done is, instead of writing is K and K here, written K plus Q, because you can in principle not only have these changes occurring in the spin orientation, you can also have changes occurring in the K value. So if you go from K state to K state, it doesn't help. You have to go to some other state so that you can cover all Q values, which are so-called K prime minus K, right? For example, if for X-ray diffraction, what is the value of Q? What will be the value of Q for X-ray diffraction? Q has a finite value because K and K prime that is the incident and the reflected ray, they may not have the same magnitude wise, they have the same K value, but the direction changes because of the reflection, right? So if I have to calculate Q, it will have finite Q, and Q, as I told you, would be equal to 4 pi by lambda and sine theta by 2. That would be the Q value. And that Q is coming because of the change in the direction of K, not in the magnitude. Magnitude is the same. So X-ray diffraction is a quasi-elastic scattering. Okay, it's a quasi-elastic scattering where the initial energy, which is given by h cross square k square by 2m, the final energy, if it is h cross square k prime square by 2m, they are equal because k equal to k prime. So there is no energy transfer in the X-ray diffraction. Okay, so now you write this perturbation Hamiltonian in terms of the creation operators and annihilation operators like this. So in the absence of this perturbation, we have only conduction electrons and magnetic these localized moments. That's all that we have. So in that case, if there is no this perturbation, then conduction electrons will be completely unpolarized. There is no particular quantization axis for conduction electron spins. So that ground state for the unpolarized conduction electrons, that we write as 0 in the Dirac notation. Now ground state for the unperturbed total system where conduction electrons and magnetic ions do not interact, okay, in that case is denoted by this 0 colon F, and that would be just simply the product of these two states, because if there is no interaction between the conduction electron spins and the spins, localized spins, impurity spins, okay, so then the wave function for this ground state wave function for this system which comprises conduction electrons and magnetic ions would be just simply given by this, which will be a product function, that is just the electronic part, the conduction electron part, and the 4F, that is the localized moment part, okay, where they will be antiparallel to each other. So depending upon the distance between the localized moments, the moments would be either ferromagnetally coupled or antiferromagnetally coupled. This generates actually competing interactions in a system like for example RKKY. I told you one example is gadolinium, where it stabilizes the ferromatic order in the ground state. Okay. Other example of RKKY is that as I said, you are dealing with a system where in gadolinium, it's not like magnetic impurities are very, very small in number. You have this 4F state every atom, right? Every gadolinium ion in the gadolinium metal, that atom has the same 7 by 2 Bohr magnetons, or 7 Bohr magnetons, 7 Bohr magnetons, magnetic moment. It is true for all the states. But there, between the states, between the 4F localized moments, the distance is too large for any overlap of the 4F wave functions to be there. So hence, there is no possibility of direct exchange, coupling the 4F spins in gadolinium. It is operating through the conduction electrons of gadolinium itself, because there are no other system. So conduction electrons of gadolinium are mediating magnetic interactions between the 4F moments in gadolinium, and hence then prefer, because of the distance between them, it prefers a ferromatic order in the system. So that's how the ferromagnetism is stabilized in gadolinium. But there are cases where you have RKKY interaction in the true sense of the term, the way I have formulated it here. That means you start with a non-magnetic matrix, okay, it's metallic matrix, and then you plant some impurities, but the concentration of impurities is negligibly small, it's very, very, very little. So that there is no probability whatsoever of finding two magnetic impurities next to each other. Okay, so that the direct exchange is not possible. Now in a spin glass, okay, where you can take the case of copper manganese, for example. Copper is diamantic matrix and you put manganese impurities. Okay. Now what will happen is, depending upon the distance between these impurities, the conduction electrons of copper would mediate interactions between these manganese ion magnetic movements. Okay. And depending upon the distance, because the distance will not be fixed, because when you put in impurities, they will not land in perfect lattice sites everywhere. So there will be disorder in the location of these magnetic ions. So then what happens is that some ions will see ferromantic interaction, other ions will see antiferromantic, and so on. Okay? So then some given spin may get these dictates from other spins. One spin says that you should align like this, other spin says no, you aligned like that. So then these competing interactions give rise to frustration when the given spin at any given site does not know which way to point, this way or this way, because there are dictates both ways and it has to satisfy both the constraints simultaneously. So it doesn't know what to do. So it flips between one and the other. So that is called the frustration. So then it leads to spin glass state at low temperatures. Below a certain temperature, freezing of spins in all random directions takes place and you get a spin glass. So it has that thing also. Now there are other aspects to it, which I will go quickly because time is running out. Okay. Another aspect that we saw is that, see, this J RKKY was proportional to J square. If you look at the thing, it goes as J square. So it's a second order effect. It's not the first order. That we have seen, correction to energy is only in second order. First order correction is 0, right? So it goes as J square, so it is a second order effect. And also, if I look at this function, for large x, how will it go? For large x, this function would be, what form it will have? What functional form will it have approximately for x? For large x? Yes? 1 by x cube, obviously. So, this RKKY interactions as a function of distance would decay as 1 by Rij cube. Okay? So it has almost like a dipolar interaction. Dipolar interaction also falls off as 1 by R cube, right? So it has that form. Third thing is that it also depends sensitively on the conduction electron density, that is Ne is the number of electrons per unit volume. Okay? So you know that this relation you know, Kf, between Kf and Ne, and you see that there is a problem here, but this is Ef is your h cross square, Kf square by 2m star. Okay? So that would be just simply it goes as Ne raised to power 2 by 3. And JRKKY then would be proportional to Ne raised to power 4 by 3. So it goes as the conduction electron density raised to power 4 by 3. Okay? So that much for the RKKY. Okay? Now we go to, see, RKKY interactions will be present only when we are dealing with metallic systems, where there is a possibility of having free electrons. But if I am dealing with magnetic oxides or fluorides, which are insulating, there are no free electrons, right? There are no free electrons there. So you cannot have RKKY interaction which is mediated through these conduction electrons when the conduction electron density is 0. So RKKY cannot operate between the magnetic ions in a magnetic insulator. Okay, for example, now you can see it. Then there has to be some other interaction also. Another important thing is that if we are dealing with these systems, these magnetic oxides or difluorides, which are these manganese oxide, nickel oxide, manganese fluoride, iron fluoride, cobalt fluoride, all that, remember that these, okay, so then this equation, this equation now can be written like this, and this gives me now chi 1 by chi 2 is minus tan theta by 2. Okay. So the normalized state is just given by this sin theta by 2 minus cos theta by 2. Okay. Now we write the explicit forms of the wave functions representing various configuration of p electrons. Okay. What are the different possibilities? First, both p electrons considered to be distinguishable reside on the diamantic O2 minus ion at anion. Okay. So that means you have manganese fellows are sitting in where they are supposed to be at R1, R2, and the two resident the electrons with spins antiparallel to each other are residing on O2 minus. That is what this configuration is. So this state would be a product state of the state where R1, remember what is R1, R2? R1, R2 are the coordinates of the p electrons, right? Of the p electrons, capital R1 and capital R2 are of that of manganese 2 plus ions, right? So now this fellow is at R0. R0 was is the position vector corresponding to O minus, right? O2 minus. So we have this as a product wave function. That means you have this corresponds to the state when one of the p electrons is at R1, the another one is at R2, but this fellow has a spin down and this fellow has spin up, right? Because they have to be antiparallel all the time because they are the resident. Now next, this will, let us say this has some energy which is just E epsilon, okay? This has that energy, okay? Now one of the p electrons is on the manganese 2 plus side, cation 1, that is via R1. So you see this, now this is at R1, again with this and down spin, and at R2, R2 is still at R0. Okay, it is this is the p electron, one of the electrons, p electron is at the p side. Okay, and that is with the spin up. So now this obviously, when this electron is at the manganese 2 plus side, that is this one will cost energy because there will be a Coulomb cost that you have to pay, right? Coulomb cost is there, although the Pauli exclusion principle would favor it because they are antiparallel, but Coulomb cost has to be paid. There will be on-site Coulomb repulsion, right? And so then that, with respect to this state, this energy, now the energy would be E plus U. Energy of this state would be E epsilon plus U. U is the Coulomb repulsion energy that the p electron experiences due to the d electrons and the manganese cation, right? Now another possibility is that one of the p electrons is on the other manganese 2 plus cation. Okay? It will be similar to the earlier one. The only thing is that now it is at R2. See, now this R1 is at R2. It was at R1 earlier. Now it is at R2. And same thing, it is spin down at the other p electron is still at R0 with the spin up. So this case is exactly the same as the earlier case, right? Only thing is that we have taken one p electron, put it on the manganese ion, that is 2 plus, on one side, on the other side, individually. So the energy cost is the same because it is just lifting one p electron and putting it at the site of manganese 2 plus, it gives you, you have to pay a cost of some energy which is U, the on-site repulsion. Okay? So it is exactly identical to that. So obviously this energy would also be epsilon plus U. Now the other possibility is when two p electrons reside on two manganese 2 plus ions. Okay? Both of them have gone to the manganese, two manganese sites, two plus ions. So then this would be the ground state, this will be the ground state where this p electron is at R1, one of them, the other one is at R2, but now at R2 the spin is with respect to that angle. Okay, that is what we had found out when that we took the projection between the sigma dot E and then tried to calculate what orientation should be the orientation of S2, and then with respect to that what would be this orientation. So this orientation would be antiparallel to that, but S2 can have some other orientation other than what you had at S1, which was taken to be Z axis. Okay? So you have this. So here we say that you have to pay some additional cost of energy, which is energy required to keep S2 at an angle theta, okay, with respect to S1, which is along Z axis. So now we have these states 1 to 4, they form a complete basis set, and hence the eigenstate of the Hamiltonian is a linear combination of these states. Okay? So now the matrix elements, between 1 and 2 state is also 2, 1, again 1, 3, because 2 and 3 are exactly same. Okay? So 1 and 3, 3, 1 will be giving the same result, which is T. T is nothing but the transfer matrix element, because it is the one where it relates to the hopping of these p electron either to the one side, to the other manganese 2 plus side, or both at a time. Okay? So that's why it is called the transfer element. But this is small because there is always a cost of energy that you have to pay whenever the p electrons are hopping to the manganese 2 plus side. Understand? Some energy cost has to be paid. So in that sense, this matrix element, it cannot be very large. It is small, has some small value. Now similarly, we have to go through that, then it will be more clear. But yes. Can you repeat it? I am not able to hear you. No. Direct, there is no possibility of direct. It has to be through the intervening oxygen 2 minus. Because as I said, the manganese 3 plus and 4 plus ions are far apart. So there is no the possibility of the overlap of manganese 3 plus, manganese 4 plus wave functions on the neighboring sites. There is no possibility. So there is no direct exchange, cannot operate. Super exchange doesn't operate because of the fact that, you see, you remember what was the problem with the super exchange? Because we had the same valence states this side and that side. That means I was dealing with either manganese 2 plus or manganese 3 plus, 4 plus 4. If you had some systems where you could have such things, then if the valence state is same, then what happens is that then this hopping to the O2 minus side is most improbable, because there you have to pay both Coulomb cost plus the exclusion principle. That is, you have to pay both the costs. So that is highly improbable. So if this does not hop, then that's why they are insulators. There is no possibility of conduction to take place. There is no conduction electron. You understand? Now here in the double exchange case, there is a possibility of hopping that is created by the fact that this fellow is empty. So this guy can come and jump through this and then come here. And in the process, it is preserving this direction. So that's why they are ferromagnetically coupled. You understand? But the real hopping is taking place. So that means there is some conductivity. It's not an insulating state. So, for everything, we cover the first two. Okay. So, what is magnetocrystalline anisotropy? Okay. This is an experimental observation that people have made, that if you have single crystals of iron, cobalt, nickel, for example, single crystals. Why single crystals? Because then you have well-defined crystallographic axis and you are in a position to apply magnetic field along specific crystallographic axis. That is the reason for a single crystal. So what people have seen is that in the case of iron, BCC iron, the easy direction are the cube edges. That is 1, 0, 0, 0, 1, 0, 0, 0, 1, 1 bar, 0, 0, 0, 1 bar, 0, 0, 0, 1 bar. So there are 6 orientations which are the cube edges, A, B, C, and minus A, minus B, minus C. So all that they have, if you apply field along any one of those 6 directions, then the magnetization saturates very fast. That means you require very small field to saturate magnetization if the field is applied along any one of those 6 directions. And these directions are called easy directions because it is easy to saturate magnetization along those directions. But if you choose the field direction to be different from the cube edges in iron, for example, if you take it body diagonal, which is 1, 1, 1, then those directions, combination of 1, 1, 1s, they are all hard directions. That means it's difficult to saturate magnetization along that direction. You can see this here. Whether it is 1, 1, 1 or 1, 1, 0 direction, it is very difficult to, you require some hundreds of oersteds to saturate magnetization in single crystal iron. Now if you take the case of nickel, it's just the reverse. That means here the 1, 1, 1 direction is the easy direction and the cube edges are hard directions. Okay. In the case of cobalt, okay, first thing I want to emphasize is iron is BCC, nickel is FCC, cobalt is HCP. Okay, it has these are the crystallographic okay. So in this cobalt, what we see is that if you apply the magnetic field along the C axis, then the magnetization saturates very fast. But if you apply field in the AB plane, in any direction in the AB plane, all those directions are equally hard. Okay, all those directions are equally hard. If I just put it in some other, in the AB plane. Okay, any direction here would be a hard direction. So this was an experimental observation. Now the question is, immediately you can see there is something that makes magnetization to prefer certain crystallographic directions in the absence of any external magnetic field. Okay? So something is holding them in that particular direction. Obviously, if magnetization is preferring certain crystallographic direction in the absence of an external magnetic field, that would mean that there should be some effective field that is holding magnetization in that direction. Now that effective field should arise from what? Should arise from some sort of a magnetoelastic coupling, right? Because there has to be some coupling between spins and the lattice. Otherwise, there is no reason why magnetization should prefer a crystallographic axis as easy axis and should lie along that, right? So there has to be some coupling between the spin and the lattice. Okay? So this is obvious from this itself. Now let us see if okay. This I will not go. This is just to show that you have to do work. For example, if I apply a magnetic field, if I apply the magnetic field in the easy axis direction, then magnetic field doesn't have to do any work because magnetization will saturate immediately. Okay? But if I apply the field in a hard direction, then obviously the magnetic field has to do work against what? The anisotropy field. Because it has to try to take magnetization out of the easy axis and try to orient it along its own axis. So in the process of magnetization, field, external field has to do work, and that is work done. So that can be just shown very clearly. And this is what the field, anisotropy field, that you will have to apply to be able to get the magnetization out of the easy axis along the field axis, where it saturates finally. Okay? So this is this. So unaxial anisotropy in cobalt is very high. It's of the order of 4.9 in 10^6 erg per cc. So this is just to give you some idea. I could have done this. You can see one more thing. When it comes to iron, you require fields which are very, very small, extremely small, right? Even few tens of Oersteds would be enough to saturate. Okay? And this, if it is in the hard direction, then you require something like 600 Oersted for iron to saturate. Okay? For nickel, this field in the hard direction is comparable. It's not very far. It's about 300. But look at cobalt. In the hard direction, it doesn't get saturated even at 0.8 Tesla. You have to apply even few Teslas to be able to see saturation, right? So what does it mean? It means what? The work done by the field goes on increasing as you go from nickel to iron and then cobalt. Cobalt is an order of magnitude higher, as you see. You need few kiloarsteds to get to saturation, whereas here tens, hundreds of Oersteds or tens of Oersteds, right? So that is the one important. So that means the anisotropy, as you go from iron to nickel, the anisotropy is a slight decrease in anisotropy, and then looking at magnetization, right? Now what you are doing is the crystalline electric field is already there. It is present and it has the same symmetry as that of the lattice. So if it is in certain direction, it locks the orbit, orbital angular momentum, and hence the orbit. And if the spin orbit coupling is strong, then it locks the spin direction also. So now the spin direction is along some crystallographic axis, which is there in the absence of the magnetic field, any external field. Is this clear? So the origin of magnetocrystalline anisotropy is the crystalline electric field plus the spin orbital interaction. Understand? Only then it is possible. Now let me go quickly through this. I have just 5 minutes, right? Okay. So the total energy is now, this is the exchange energy, Heisenberg exchange. This is magnetocrystalline anisotropy energy. This is magnetostatic energy, and this is the magnetoelastic energy. Okay? Magnetostatic energy, do you know what is magnetostatic energy? Magnetostatic energy, any idea? Yes? There can be volume charges also, magnetic charges, not only surface. Surface is induced because of the magnetic field. But we are dealing with not in the magnetic, it's the absence of the field. Okay? So what is magnetostatic here? Because you are always dealing with magnetic dipoles. So dipole-dipole interaction will always be present. Okay? So that is what is manifested when you apply a magnetic field. Then you see, depending upon how many what is the induced pole density. That would depend upon the area, cross-sectional area that is exposed to the field. If I am applying the field like this, then the cross-sectional area that is exposed to the field is this. So the number of induced poles here is going to be smaller than if I now turn it like this and then I apply the field like this, so that the cross-sectional area has increased several folds. So that means if it left to the shape, then easy direction of magnetization would be this. It will not be this. Okay? So this you are able to see when you apply the field, but it is already there because we already have magnetic dipoles inside. They are trying to, dipole interactions will try to orient dipoles in some direction, right? So that's why this magnetostatic interaction is nothing but a basically dipole-dipole interaction in the absence of any external field. That will also try to orient the, for example, if you have a system like this and there are dipoles, dipoles will also try to orient in some direction, which will be some easy direction which is according to the magnetic dipole interaction. So let us see now, that would be more clear. So equilibrium state of the system is when this total energy is minimized. Now if I start with, let's say, I say that my single crystal is a single domain sample. Okay, so there is only one domain. Then what will happen is I have now all magnetization pointing like this within that whole sample. All the spins are going like that only, and in this configuration the exchange interaction energy is minimum because the spins are parallel to each other. When it comes to the anisotropy, this happens to be the easy direction of magnetization. So no problem, the anisotropy energy is also minimum in this configuration. But then the problem is this, because now when the magnetization vector, they are pointing like this is now the domain resultant magnetization. This is pointing like this. So then there are these south poles, north poles induced here. Okay, so now there is this possibility of these field lines going like that, even in the absence of any external magnetic field. Okay, so because of these lines, they give rise to a large magnetostatic energy. It's a huge magnetostatic energy. So the energy is not minimized yet, but now you see, if I now divide the sample into two domains like this, which are 280-degree domains, then what is happening is that whatever you have north-north, south-south here, north here, so these field lines are getting closed there itself. They are not going anywhere. So just by creating one domain wall and dividing it into two domains, the magnetostatic energy has reduced by a factor of 2 roughly. Okay? So now what will happen is that in the process, but I have created this wall, domain wall. Now in the domain wall, magnetization has to go, in the domain wall here, magnetization has to go from this orientation to this orientation. It has to go from this to this orientation. So as the magnetization within the domain wall moves out of this direction, goes like this, there, this is the easy direction. And this is also the direction where, okay, first let us see the easy direction. So then there is an energy cost. That means there will be a slight increase in the anisotropy energy, right? At the same time, now the angle between the successive spins is not 0. It's a finite angle, because this one spin goes like this, the another one is going further, tilting. Okay? So this angle is not 0, it's some finite value, maybe small but finite. So there is some the exchange cost of energy, right? So exchange energy would increase a little bit, the anisotropy energy would increase a little bit, but the decrease in the magnetostatic energy is huge, a factor of 2. So two domain configuration would be preferred over single domain, and the division into different domains will go on occurring as long as the energy cost that you have to pay for creating these different domain walls, okay, that energy cost is in terms of the exchange energy and anisotropy energy, okay, and there is a corresponding reduction in the magnetostatic energy, and when this trade-off takes place, theta is the width of the wall is proportional to 1 by root k. So that means as the anisotropy constant within the it decreases with temperature, so the wall width would increase with temperature, right? Till at Tc, it is like a domain wall itself. There is no domains, so that's why it's completely disordered. All orientations of spins possible. Okay, and this just to give you this idea that when you now plug in this expression, you plug in the equilibrium value of the wall thickness, which is this, then you end up like this, which shows that at equilibrium, it prefers that the exchange energy and the anisotropy energy should be same. Okay, it is seen here. One goes as 1 by n, another goes as n, and so minimum is occurring where they cross each other. So that means they have the same value at that. So that is the equilibrium value of the domain wall width. Now just for your just to give you an idea, okay, let's say for iron, J is roughly this, and these are the lattice parameter value of K at room temperature. This is the Tc value. If you plug in these values now, what you find is that the equilibrium domain wall width is of the order of 300 angstroms. Okay, and this corresponds to, the number of atoms you are asking. So this corresponds to this divided by lattice parameter value. So that gives me about 120 atoms. So there are 120 atoms with spins which are there within a wall, domain wall. Understand? Domain wall energy, you calculate same way. You calculate, you will get something like 2.9 ergs per centimeter square, because it is domain wall energy per unit area. Gammas are like that. Now let's go to nickel. You see here the anisotropy has reduced by one factor, and Tc is lower, of course. A is comparable, it's not so different, but then this delta is 290 atoms from 120 in iron. Iron was 120, nickel is 290. Okay, and this energy, this wall energy, is now 0.7 ergs per centimeter square, which will be square here. Okay, compared to 2.9, that is roughly 4 times smaller. Right? So this gives you an idea. Okay, so I think I'll just quickly go through this. Just 1, 2. So now in the case of domains, now you saw that the multi-domain structure is naturally occurring in any of these ferromagnets. Okay, so then the question is, how do we now relate it to the actual measured data? That means you always measure isotherms and measure magnetization as a functional field at fixed temperatures. You do that, move. So it's like a creep. This just creeps like this and then goes like that. Then, so the increase in magnetization is in steps. Okay, so field will do it like this, and the movement will move. It's not continuous. So how fast or how slow it will be, and in what form it would be, would also be dictated by if there are some impurities, imperfections in the lattice. So that will also pin the domain wall. Understand? Apart from the energy that I considered,